Okay, I would like to introduce the new features of the Mastodon Deep Lineage 0.1.1 release. And I will start with the new feature import spots from label image. In order to demonstrate this, I have chosen this dataset from the Cell Tracking Challenge. It's publicly available and can be downloaded from anyone who has access to the internet. I'm using this training dataset, so I've downloaded it already, and I will now import the grayscale image from it. That's contained in the folder training01, and it contains 12 TIFF files, so which encodes 12 time points. And I need to set the image properties. So the slices in this case is 30, and we have 12 time points as already set. Once I've set this information, I can open the Mastodon plugin for Fiji, and I can then create a new project based on this image in ImageJ. I can open the big data viewer, and the big data viewer would show the image data, as you can see. I can zoom through the image. And I can also open the track scheme window. In the track scheme window, you see that you do not see any spots right now. In the case of this image data, we have a segmentation, and I will now open the segmentation. Segmentation is contained in this folder, and we would need to set the image properties again. So that's 30 slices again and 12 time frames again. And now we can use this segmented image data with the new plugin for Mastodon. Imports spots from label image, and then we choose import spots from ImageJ image. It opens up a new dialog. There we can enter an ellipsoid scaling factor. We recommend to use 1 as a default, but if you choose values higher than 1 or lower than 1, you can increase or decrease the resulting ellipsoid sizes. And for very specific scenarios, you could also decide to link spots which have the same label ID in consecutive frames. I will leave this option deactivated for this example, since this segmentation or the segmented data for this data set does not have spots which have the same labels in consecutive frames. So I would press OK here, and then it would import all the ellipsoids. We can see them in the big data viewer. We can also see them here in the track scheme. After we have imported all the spots, we can also link these two windows with each other. And then if we go through the track scheme and just click on different cells at different time points, we can also see them highlighted in the big data viewer. Now we could use the linker in Mastodon to automatically link these imported ellipsoid data. Maybe just a few words to explain how this import actually works. You can see here in the big data viewer, so I have now imported the image data again, but with two channels. Channel 1 contains the grayscale image data, which you can see as the red channel, and channel 2 contains the segmentation data. And this segmentation data is actually processed, so pixel by pixel, and all of these segmentations, they have one common pixel values, and from these distribution of these pixel values, you can compute a variance-covariance matrix, and from this variance-covariance matrix, you can derive the ellipsoid parameters, so the free axis and the center of the ellipsoid. Okay, the next new feature in the new release is the feature to export the branch graph to a GraphML file. I'm going to demonstrate this with this example dataset that you can see here. I have opened the branch view window, so that's this one, track scheme branch, and I'm going to export GraphML branches, and I have, so here you have three options. One option is that you export all branches that you can see to one single GraphML file. The second option is that if you've made a selection before, you could say only the selected branches to the GraphML. Or the third option is that you export the tracks to GraphML, and that would result in one file per track. So for all of these cells, that would be considered one track or one sublineage. And this would be exported to one separate file. So I'm going to show you the case with one file. It is recommended that you name this file with the extension GraphML in the export dialog. And once you have exported this file, you can, for example, import it in a software called Wired, openly available software for graph processing. And for example, you can here now set a directed layout. Then you would see the layout, and if you want to see the branch names again, then you could take the properties mapper and take the branch name here and set the label text. And then if you apply this, then you will see the spot names again here as well. And you have then different possibilities of designing the trees. So that may be useful for if you want to prepare your branch data for publication. Okay, and now I would like to introduce the next new feature with the new release, and that's the movement relative to neighbors. And for that purpose, I have designed little test data sets in order to exemplify this. And as you can see here, this test data set contains 6 spots in total. 5 spots are here and 1 spot is here. And if we move forward in time, you can see that they move in opposite directions. So these 5, they move in this directions to the lower right, and that one moves to the upper left. And the movement relative to neighbors features is a feature that can capture this behavior numerically. You find that new feature not in the feature computer as all the other features, but in the menu under compute features, movement of spots relative to nearest neighbors. And the reason for this is that other than the normal features, so to say, they don't have parameters that can be set by the users. This feature, the compute relative movement in relation to nearest neighbors, has a parameter where you can set the number of nearest neighbors to be considered. I will leave it here for 5 because also this example, as you can see, is designed for these 5 nearest neighbors. I will press OK. So you can see here that in the table, here you can see it, there's new columns, spot relative movement. It captures the X, Y, and Z component and also the total distance of the relative movement of all the spots. And similarly, we have for the branch spot, we have also average speed. We called it here because it captures the movement of the whole branch, and you could consider that as the average speed. And you have it in all 3 dimensions, and then the total average speed. Okay, and you can also now use these values to visualize them in Mastodon. And for that purpose, I go to File Preferences, Feature Color Modes. I duplicate an existing one, rename it to Relative Movement, call that Relative Movement on spot level. You will see in a second that there is also a feature color mode, Relative Movement on branch spot level. Then I have to select the features, so that's the spot relative movement. Then I take the total distance to the 5 nearest neighbors. I select auto scale, and for the links, I want to have the same settings. So it's select copy from spot settings, so I get the same settings here. I do apply, and now I can, in the view, I can select this as the view color mode, and as you can see here, that this captures nicely and also numerically shows that this spot has really different values than the other ones. And you can also visualize it in the track scheme. So you can also see here that the color is different. This black means that no movement could be calculated because the first spots, they do not have a predecessor, so there's no relative movement possible to be computed. And you can also see it here. So that's the same. And yeah, these color or these rows here are the rows that refer to that one that moves in the opposite direction. And the same is also possible for the branch spot. So we could do a new feature color mode. We call it branch spot. Branch spot. Then we select here branch spot. We select the relative movement. We take the average speed. We make auto scale again. Then we copy from spot settings and we apply. And then we can open up a BDV branch view. And in that BDV branch view, we see the spots at this time point, and we can now select the branch coloring. And that's the relative movement setting that we just did. And you can see here that also here you can see that this spot which moves in the opposite direction can be identified very well. And yeah, it would also be possible here in the table. Could also say here branch coloring, and then you would identify this one. Okay, that's it.